Well, I can't see the buttons. Okay. You let me know when we're on. You guys are gonna let me know when we're on, eh? Oh, we're on. Okay. Well, welcome to our webcast tonight from Learn America, and we are here to basically talk a little bit about the chemistry necessary to be able to excel on the New York State Regents exam. And today what we're going to do is we're going to focus in on the fundamental particle, which is the basis of chemistry. So, we're going to talk atomic structure. And in order to appreciate why you need to know about atomic structure, it's almost as like when you go to a Lego store. And everyone's familiar with Lego stores, that when you enter into the Lego store, the store is surrounded by all different colors of Legos, sizes of Legos, and the most exciting thing that you just want to do is to start to build things with these Legos. But you'd notice that the Legos start. Remember when it was Christmas time when you were 3 years old and the first Legos you got were extremely large, and then as you got older, every Christmas you would get a set of Legos that was smaller and smaller and smaller, and then eventually you ended up getting your hands on those really tiny Legos. But you realized that with those little tiny Legos you can build larger Legos and eventually build whatever your little heart desires. So that's the most important thing about understanding atomic structure, because that's what chemists do. They play with their atomic Legos and build whatever they desire with those atoms. But to understand the atom, you have to first understand the fundamentals of charges, right? For example, we all know, well, hopefully we know, that like charges repel. So if something has a negative charge and something else has a negative charge, they'll repel each other. If we have a particle that has opposite charges, they will attract. But there are some things that we might not understand that are very fundamental in the understanding of an atomic structure, is the fact that when particles that have charges are in motion, they are actually create magnetic fields. And that means they act like magnets. And as we all know, when you have two magnets, and sometimes when you place them in a certain orientation, they're attracted. But if you spin them in a different orientation, they repel. Well, that's because those magnets are creating magnetic fields. But these charged particles that we're going to talk about today follow the same concept. Once they're in motion, they act as magnets. So if you put them in what they call a magnetic field, they're going to be affected by that magnetic field. I like to start all lessons with a phenomenon and then go back to the phenomenon and try to see if we can explain the supposed magic trick. So we're going to take a look at these magic balloons. So what I did is we have a quick video on a demonstration that I think is quite interesting and quite popular. You probably have done this demonstration at home. Here we have a balloon, okay? And what we're going to do is we're going to, on the surface of the balloon, we're going to rub it with a microfiber cloth, and then basically place objects next to the balloon and see what happens. And we see something very strange occurring. Again, our goal is to understand, how did that happen? How is that happening? Okay? And in the next video, what we're going to do is we're going to take two balloons, and we're going to take those two balloons and we're going to put them next to each other, and we notice it's like a magic trick. There's repulsion of some sort, right? And then this time, we're going to rub both balloons, and we're going to see that they repel each other. The question is, why is that happening? What is the science behind that? So at the end of the presentation, I'm going to ask you if you can answer what's behind the phenomenon. Okay, what was causing the balloons to move the way they were moving? Okay, and it's going to basically be related to what we just discussed. What's behind this is the science of the atom. But to understand the science of the atom, you have to understand the history of the atom. Now, the history of the atom goes way back into ancient Greece, where a famous philosopher called Democritus had an idea. He believed that the atom was a hard sphere. Okay? Envision these tiny, tiny, tiny marbles. And he believed that these tiny, tiny marbles, and we say, how small were these marbles? Let's think of a grain of sand. And he believed that if you took these particles and put them next to each other, you could create all different forms of matter. Now, what's interesting about this, the origin of the word atom comes from Democritus, who basically said that these atoms were the size of tiny grains of sand. But what was unique is that these hard, tiny sand marbles could not be broken down. And the Greek word that basically describes that is the word atomos. So the history of where the word in the atom comes from is from the word atomos. But in ancient Greece, it was all about popularity. And another famous Greek philosopher, Aristotle, basically squashed his theory of the tiny marble hard sphere theory. And he came up with, now we can laugh about it, but he basically believed that matter was made up of 4 concepts: fire, air, earth, and water. And if you blended those things, you could create all different forms of matter. Now we could laugh about it because we've learned some chemistry, but the moral of the story, Democritus' theory got squashed. And this theory actually stood through the Middle Ages. It wasn't until the late 1700s, mid-1800s, with the work of 3 main scientists, Lavoisier, Proust, and Dalton, who basically created a rebirth of the hard sphere model. Now, it's very important to follow this history because the Regents will ask you a sequence of the history of the atom, typically in a multiple choice question, which we'll see later on in the presentation. But these 3 scientists basically brought back the idea that these atoms, which that's what they called it, were these tiny spherical particles that make up what we know today as elements. Now I'm going to show you a really neat video by Learn America, which they basically took Dalton's theories and the theories of the other 2 scientists, put it together so that you can enjoy a quick review.
John Dalton is called as the father of modern atomic theory. Nearly 200 years ago, he postulated his atomic theory. He insisted that all matter was made up of atoms. He was able to imagine atoms even though he could not see them. This helped him to formulate his atomic theory. He described atoms as small, rigid balls. He also said that atoms were indivisible. He supposed that there were many types of atoms.
You should note, though, that in Dalton's theory, all the different elements had their own different types of small spheres, and that's what distinguished one element from the other.
Moreover, all atoms of the same element are identical. They have same mass and properties. This theory was the beginning of atomic theory of matter.
So, what's also key is that he believed that all the helium spheres were identical. And he believed that made each element unique. Later on, we discovered that that wasn't 100% true. That wasn't 100% true. But what also, he is the father of the compound. So when we defined elements and compounds, he was the one who basically stated that if you take these spheres and place them, different spheres from different elements, together, you would create compounds. And when you created those compounds, you would follow the law of definite proportion. For example, a water molecule, in order to be water, would have to have 2 hydrogen spheres connected to 1 oxygen sphere. And that was the law of definite proportion. He was the father of that concept. And we're talking in the early 1800s. So the law of constant composition, which means if you had water, this is based on mass, for every 1 gram of hydrogen, there would have to be 8 grams of oxygen because of the ratio of these spheres. It wasn't until around 1897, a famous scientist called J.J. Thomson was experimenting. Now, you have to understand that the ancient Greek philosophers, the reason why we didn't call them scientists, because they didn't experiment. Dalton, Proust, and Lavoisier were chemists and scientists and physicists because they experimented in order to come up with their hypothesis and their theories. So what J.J. Thomson did, he gets credit as the father of the electron. What he did was a very interesting experiment. He created a tube that basically had nothing in it, a vacuum tube. And this vacuum tube, what basically had on one end was a piece of metal that was charged with a particle that this piece of metal had less of. When you built up what they call enough potential difference in that charge, he discovered an interesting phenomenon. He discovered that there was a beam of particles that moved from the high potential to the low potential, from the negative end to the positive end. What this particle was able to do was move through space. Then he performed the experiment. He wanted to understand what charge that particle had. And by the way he was able to do that, he took another electrical field and placed it in the path of these particles. And he saw that the particles were attracted to the positive end of what they call an electric field. He continued his experimentation with all different types of tubes. And what he discovered, that these particles could be absorbed by matter. In fact, the matter that he used, like zinc sulfide, would glow whenever this beam would hit it. Turns out, he was not only the father of electron, but what he was able to come up with is the basis of what we used to use as computer monitors and televisions. The screen on the front of that computer monitor was being struck by these particles. And he was able to control the particles using electrical circuitry, not only with electric fields, but also with magnetic fields, so you could control where the beam would go. So he was kind of like the father of our computer monitor. But what was interesting with this theory, and in science this always happens, they wanted to understand the structure of the atom. So J.J. Thomson came up with a model. His model of the atom was called the plum pudding model. But there was issues. We still didn't know where the positive charge inside these atoms were. During this time period, scientists were discovering another particle existed inside the atom called a neutron, but the neutron had no charge. At the same time period, scientists were working with materials that were referred to as radioactive. These atoms had an imbalance of proton-neutrons inside them. And because of the imbalance, pieces of their atoms were coming out of materials that were called X-rays and gamma rays, which are basically high-powered, what we later found out called photons. There were things called alpha particles that could come out of an atom. And there were things called beta particles, which were basically high-speed electrons that could come out of an atom. But this would come out of certain types of atoms, which we now know we call them radioactive atoms. Because they're radioactive because they have the improper proton-neutron ratio inside them. So, at the same time period, another famous scientist was working with these supposed particles that Thomson was working with, and what his name was Millikan, Robert Millikan. And what he discovered was the actual charge of an electron, that an itsy-bitsy particle, which was later called the electron, carries with it a certain amount of charge. And he was able to do an interesting experiment by understanding that each of these particles, once they are having a negative charge, you can actually have matter absorb them, and you could actually make matter float by using electrical fields, which is pretty neat. But again, there was really no true foundation of the atom. In fact, the model that J.J. Thomson came up with was called the plum pudding model, which he believed that the atom was like pudding with little electron raisins sitting inside them. And if you took this blob of pudding and put it on another blob of pudding, it would stick. And you could make matter with that. Obviously, today we laugh at that. But during that time period, they didn't have the type of technology that we have today. But it was a model. And Ernest Rutherford, a famous physicist in 1910, was set out to basically come up with experiments to prove whether the plum pudding model was correct or incorrect. And he used this radioactivity, these particles that come out of these atoms that are unbalanced inside their nucleus. And the particle he chose was the alpha particle, which basically comes from atoms that have more than 83 protons inside their nucleus. And what he did, he came up with the famous gold foil experiment. What he believed was that if J.J. Thomson was correct, he was going to basically fire these alpha particles at a very thin, at the atomic level thickness of gold. Now this foil is so delicate, if you were to touch it, it would disintegrate. So what he thought, if the plum model was correct, he would shoot these alpha particles that would come from like a source like uranium, and it basically would go right through this gold foil. The question is why? Well, if the alpha particles are basically the size of a helium nucleus with a positive 2 charge, and the plum pudding is what made up that gold, the pudding part, that's the positive field, would separate because it would be repelled, and the alpha particles could go right through the gold. Unfortunately, that's not what happened. So once he was able to shoot these particles, he believed that he would be able to go right through the plum pudding atoms and discover on the other side would be this material that would glow once the alpha particles would hit. But that's not what happened. He noticed that some of the alpha particles went off their path, and some of them had a direct hit against a very dense area that must have a positive charge. He explained this by basically saying that the structure of the atom has a center, which we now know he's the father of the nucleus, right? That was very dense with a positive charge and contained most of the mass of the atom, right? So when he shot the particle and it hit where the nucleus was, it would be repelled and obviously go off its path. So the outcome of his gold foil experiment, he basically discovered the nucleus. And that's where those protons are. That's where those protons are inside that atom, right in the center. But he also discovered something very important, that the atom had a big volume of space. And those big, thick, large alpha particles relative to the size of the electrons could just pass right through because there was a lot of space. So, here's our first Regents question. You ready? This is what I want you to do. Okay, you have this whiteboard. Here's a you have your own personal whiteboard. You got one? And there's a marker right there. So, we're going to ask you the question. It says, in an experiment, alpha particles were used to bombard a gold foil. So the kind of thing that they're going to see and assess if your instructor basically told you the little history story that I told you. And as the result of the experiment, the conclusion was made that the nucleus of the atom is, and there's 4 choices. What's the best choice? The nucleus of the atom. Is it larger or smaller than the atom? Right? So by process of elimination, that's the first thing you have to decide. Is the nucleus, the atom, larger or smaller than the actual size of the atom? What do you think?
Smaller.
It's smaller. So that gives us choice B and D. Then the question is, what charge would it have? Right? So, I'm sorry, B is C. So it's smaller than the atom and would possibly contain all the protons, right? So therefore, what charge would it have?
Positive.
Positive charge. And that's how simple it is, but you have to know the history and the story of the atom and understand its structure. So, they believed, at this point, that Rutherford's experiment was basically telling us the core of the mass and the core of the positive charge is in the nucleus. And these electrons are found somewhere outside that nucleus. At the same time, a famous scientist called Chadwick basically discovered that inside the nucleus there were always also these particles called neutrons. And these neutrons had no charge. Now, another famous scientist who's basically directing us to the true model of the atom was a famous scientist called Niels Bohr. Niels Bohr believed that the nucleus would be like the sun in our universe, and the electrons would be like the planets in our universe. And obviously every planet travels in some sort of path, which he referred to as orbits, okay? And these orbits had what they called energy levels, or another way of looking at it, a sphere or a shell in which they would travel on the outside of that shell on this orbital path. Now, we know that that's incorrect. But what was important in his model is the fact that the electrons carry with them a certain amount of potential energy. They have a certain amount of energy. Every electron on every single atom has a specific amount of energy. And in his model, he believed those electrons that were closer to the nucleus, or closer to that sun in that universe, would have the lower amount of energy, and the further the orbit from the nucleus, the greater the potential energy of the electron. This became a critical hypothesis, which eventually developed into what we call the quantum model, which we use today. So he believed that you had this nucleus and you had these electrons that traveled in specific orbits, which these orbits had certain distances from the nucleus. So you have energy level 1, energy level 2, energy level 3, or shell 1, shell 2, shell 3, which basically would tell you the quantity of energy those electrons had. So envision a ladder, and each step of the ladder is the circular path around the nucleus, which is on the bottom of the ladder. What he also determined is that these electrons can actually move from the bottom step to the second step to the third step to the fourth step. So these electrons that had a certain potential energy, depending on what step they're on, could actually move from the first energy level to the second energy level and actually move back to their original orbit. What's important to note, at this point in the research, they had determined that protons and neutrons were very similar in mass. Now these numbers have been rounded off. A neutron weighs a tiny, tiny bit more than a proton. And there's a reason for that. Because the next question would say, well, why are the protons and neutrons inside the nucleus? Why is the neutron stay inside the nucleus? It turns out the proton is missing a piece that the neutron has. The neutron acts like the glue of the nucleus, keeps these positive protons from repelling each other and staying in this dense area. So the proton and neutrons are related to each other by that fact. Now this electron is so tiny. The proton is about 1,800 times larger than an electron. And when particles are that small, okay, they start to have specific properties that are unique to only to particles of that size. These electrons and these protons obviously carry a certain amount of charge. The unit for charge is a unit called coulombs. You don't have to know that on the Regents, but if you end up taking chemistry in college, that's something you would need to know. Here's a question. Regents question. It says, which two particles have approximately the same mass? What do you think? What letter? Choice C. That's how simple it is. Very good. Here's another one. It says, and this is all from the past two Regencies, given a list of atomic model descriptions, electron shells outside a central nucleus, hard indivisible spheres, mostly empty space. Okay? Which list of atomic model descriptions represents the order of historical development from the earliest to the most recent? Which one's first? So I had the little quick history lesson I gave you. Which one of these theories would be the beginning? B. Choice B is absolutely correct. Right? So even back from Democritus, right? They believed there was some hard sphere, and then Dalton took that theory. Then, what would be the second one? Who proved that the atom had mostly empty space?
Rutherford.
Very good. So who was first? Rutherford, and who proved the electron shell theory?
Bohr.
Bohr. So who was first, Rutherford or Bohr?
Rutherford.
Very good. So if you know the history lesson, you could follow the concept in the same sequence. So what would be the best choice? So obviously, the first one was B, right? The second one was C, and then we went to A, which was Bohr theory. So BCA would be the best choice. Right? You with me? Piece of cake. Piece of cake. These atoms are so tiny, right? We mentioned that already. The nucleus of an atom, compared to the actual volume of the atom, the nucleus would be like a marble, and you're standing in Yankee Stadium, right? The nucleus, that's how small it is compared to the actual volume of the atom. The other thing is that they're so small that if you were to want to weigh one, you could not use grams, because that would be a unit that would put you into some serious negative scientific notation. So scientists, what they did is they developed a unit just for the particle. They call it an AMU. 1 AMU is equivalent to this in kilograms. Every single atom has what we call an atomic number. The number represents the number of protons inside the nucleus and the nuclear charge of that atom. Right? This is extremely important, because this is what identifies the atom you're working with. Right? That's what identifies the atom you're working with. But every single atom also has its own mass number. That's important. You say, wait a minute, Mr. Langella, mass number? I thought all the atoms were the same. Well, that was Dalton's theory. Turns out, you could have a nucleus that has the correct number of protons, which identifies the atom, but you could have his crazy cousin, which we would call the radioisotope, that has the imbalanced number of neutrons. See, there is supposed to be a certain number of neutrons for every number of protons you have in an atom. But you could have some atoms that you could find that has the exact same number of protons, therefore be the exact same atom by identity, but be different by the number of neutrons inside the nucleus. They're called, you know what they're called even before I tell you? Atoms that have the same number of protons, but different number of neutrons. Isotopes. Very good. Isotopes. And that's why you identify every single type of atom by its mass number. The mass number is basically the number of protons plus the number of neutrons. And again, remember that the mass of the nucleus is really the mass of the atom. So let's start here. It says experimental evidence indicates that the nucleus of an atom what do you think? D. Choice D contains all the mass of the atom. Very good. So when you have an atom, to identify it, you're going to have a atomic number, lower left-hand corner, based on the Regents, this mass number in the upper left-hand corner, and the actual symbol of the atom. The symbol and the atomic number are locked. That means if this is a C, there's no doubt that it's going to have the atomic number of carbon, which would be, we would look that up, right? You have it on the Regents table, it would be like a 6. Right? So these numbers are locked. Right? But this number can vary depending on whether you have what we call the stable atom or its radioisotope. Right? So, you have in the centerfold of your Regents reference table enlarged the model for carbon. And then you have the periodic table with all the atoms on. It's important that you need to be able to decipher the model and understand what everything they're giving you is telling you. So this is the atomic number of carbon. What does the atomic number tell me? You're answering all these.
How many protons and electrons there are.
Very good. So this atomic number is going to tell me how many protons and how many electrons it should have. Because for every proton, you have an equal number of electrons. Right? Then this mass number on the upper left-hand corner. Remember that the symbol and the atomic number are locked. The mass number tells me
number of it's the neutrons plus the protons.
Number of neutrons plus the number of protons inside the nucleus. But you should note that this is not a whole number, which we're going to talk about that in a minute. Then you have these numbers in the upper right-hand corner. Very important. They're called oxidation states. What they tell you is what carbon can do. What a carbon atom can do. Well, the first number is a negative number. And what that's telling me is that carbon, the atom of carbon, has the ability to draw 4 negative charges, which we now know are those electrons, from another atom. And by doing that, it will transform itself from an atom to a thing we call an anion. An anion is an atom with a negative, an atom or a molecule with a negative charge. So an anion, what happened, you had, for example, this carbon atom, and he was able to draw 4 electrons from some other atom. But then you should note that there are other numbers. This is the most common thing that carbon will do. Typically when it interacts with an atom that doesn't have the ability to draw electrons. But if it interacts with an atom that has a greater ability to draw electrons than itself, it could, in theory, lose electrons and become more positive because the ratio of protons is greater than the ratio of electrons. Typically, when you're a nonmetal, these numbers are telling you what's going to happen with the electrons that you might be sharing with another nonmetal. They're telling you a story, which is another chapter. And then in the bottom left, based on the New York State Regents, is the famous what we call Bohr configuration. What this is telling you, based on Bohr's model, how many electrons would be in the first energy level, and the next digit would tell you how many electrons it should be in the second energy level on the carbon atom. Notice 2 plus 4 equals 6, because you told me the number of protons should equal the number of electrons. You with me? Okay. So, based on that information, can you tell me which atom has the greatest nuclear charge?
A charge?
Yeah. They're a word, it's like a word game, so you have to carefully decide, because it's which atom has the greatest nuclear charge. Well, wait a minute. What's controlling the charge of the nucleus?
The number of electrons.
I thought the electrons were on the outside. Did we do that one?
Protons.
Number of protons, right? So, which digit is telling me the number of protons inside this atom? Is it the number on the bottom, or is it the number on the top? The bottom, which is called the atomic number, right? So what's the answer? D, because it has 7 protons inside its nucleus. You with me? So the nucleus is where the positive charge is, right? And outside the nucleus is where the negative electrons are, right? So the nuclear charge is referring to the charge of the nucleus. So, again, you're going to have a symbol. You're going to have a number that's down here, which we call the atomic number. And then you got the mass number on the top, that's the protons and the neutrons. Remember that the symbol and the protons are always locked. And then I told you, well, if there's numbers on the upper right-hand corner of the atom, that you're not really looking at the atom, you're looking at its cation or anion, which is basically what happens to that atom after it gains or loses electrons. We also discussed the term isotopes. Dalton was wrong in his theory because he believed all the atoms were identical in that element. So, well, what we discover is out of so many million atoms, let's say even in your body that are carbon, there's going to be carbon-14 atoms versus carbon-12, which is the typical abundant atom of carbon. The carbon-14 is what we call the radioisotopes. A radioisotope, and its abundant isotope, were discovered using this thing called a mass spectrophotometer. A famous scientist, what he did, is actually more than one, they took the element and they charged them and passed them through a magnetic field. And what they discovered is that all the atoms are not the same. So if you took the element carbon and passed it through this instrument, you'd find that you're going to have some carbon-12, you're going to have some carbon-14. The question is, what's the difference between carbon-12 and carbon-14, right? And what does the word isotope mean? Well, we're going to find out right now. If the Regents asks which nuclei referring to a nucleus, is an isotope of this atom's nucleus, what would the correct answer be? Well, what's the key ingredient? To be an isotope, it has to have the same atomic number, right? So far, if that's true, what's this guy's atomic number? Do you know? Well, what controls the atomic number? The number of protons, right, inside its nucleus. So if you look at the symbolism, because the Regents is big into his symbolisms, this guy has how many protons? 10. So which one could be an isotope is the question. It's got to have 10 protons inside its nucleus to be an isotope, right? So choice B is the best answer right now because it has 10 protons. But the question is, why is it an isotope? What does isotope mean? By definition, same number of protons but different number of neutrons. Correct. Has nothing to do with the electrons. It's just about the nucleus, right? So this guy is the crazy cousin of that guy. If this is the abundant isotope, he's the crazy cousin. He's got the imbalance, right? That means he doesn't have the right ratio of protons and neutrons. Again, these questions are directly from past exams. So let's see if you get this one now, without my help. It says, which pair of atoms are isotopes of this supposed element X? A is correct. Very good. A is correct. Very good. All right, here's another one. Getting these all from past exams. Compared to carbon-12, that's what that means. Right? C with a 12 after, it's telling you its mass number. And that's the abundant isotope. That's the normal carbon. What about carbon-14? What does it have greater? Be careful, they set the question up to be tricky, so what's the answer?
Mass number.
The mass number, right? The mass number. Now you're going to see this question, other variations of it, right? Like they could talk about this one. Now be careful, it says, what is the number? Now, how do we know this? What is the number of electrons in an atom of scandium, right? What would you need to figure that out?
Protons.
Very good. So you look at the periodic table, right? Look at the atomic number of scandium, and that should be the number of protons and the number of electrons it should have. You with me? Okay. So, now I'll give you different variations and same types of questions and see how quickly you can come up with the answer. Here's the symbolism. Right? How many protons does it have?
9.
Good. How many neutrons does it have?
10.
Good. How many electrons does it have?
9.
Very good. What's its atomic number?
9.
What's its mass number?
19.
That's it. And you're going to get something like that. Believe it or not, you're going to get, and it's going to be you got to just carefully read the question. But I can tell you without a shadow of a doubt that given the symbolism, they're going to want to know what those facts are. Or they could give it to you this way. They say you got this element, and inside the element are atoms that have an atomic number of 34 and a mass number of 78. Right? So this time they don't give you the symbol, they just give it to you in words. Same problem, right? Same problem. Same problem. But you would have to be able to realize that I'm going to go to my periodic table and get that symbol for that element. Write it down. So this would be like a short answer question, right? You'd have to write down what's the symbol, what its atomic number, and then put in all the information of the symbol. Again, same type of question. So let's go to an actual question that's been asked. What is the number of electrons in an atom that has 20 protons and 17 neutrons? Look, again, number of electrons. 20. Very good. Here are two nuclides. That means just the nucleus of atoms. That's what a nuclide is. Vocabulary word. Right? This is carbon. This is nitrogen. This is their mass numbers. Which choice is the best choice?
D.
They both have the same mass numbers, correct? Here's another one. What is the symbol for an atom that has 20 protons and 22 neutrons? So you would go to your periodic table. Do you have a periodic table with you by chance? Okay. And you would look up who has the atomic number 20 and just match it, right, to the symbol, which is, I believe we're talking calcium, right? And how would I figure out which calcium is the correct answer? Which choice is it?
B.
B, why?
Because you add the number of protons and neutrons.
Very good. Now, the Regents is big into particle representation, okay? And they're kind of following the path of advanced exams like AP exams. So they kind of get you ready for such a thing. So they give you these pictures. They say, hey, you got 4 atomic nuclei here. And the darkened circles represent protons, and the undarkened circles represent the neutrons. Again, we're only focusing on a nucleus. So they say, identify the element that has the atomic nuclei in picture number 1. So how would you handle that?
Count the number of protons and then go into the periodic table.
Very good. So you count up the number of protons, right? And that would represent the atomic number. You look it up on the periodic table, and you basically give them the answer they want. How would you determine the mass number for nucleus number 2?
You count how many circles there are.
Period, right? Because the mass number are the protons and the neutrons. Excellent. And then they say, explain why nucleus 2 and nucleus 4 represent the nuclei of 2 different isotopes of the same element. So they're saying, why is 2 and 4 isotopes?
Because they have the same amount of dark circles, but not the same amount of hollow circles.
Right. Very good. Very good. Now, the problem with these atoms is that they're so tiny that you really can't start counting atoms in the sense of, oh, there goes one, there goes another one. You can't do it that way. They're too tiny. So what you're going to do is you're going to use mass to come up with a count of atoms. And thus the invention of the concept of the mole. You know, when you go to a bakery and say, can I have a dozen bagels? It's understood. He's going to give you how many? 12. But in the world of chemistry, 12 atoms are so tiny, you can't even work with them. Right? So they came up with their own number that replaces the dozen. Okay? This number is quite large. How large is that number in magnitude? Well, about if you had basketballs, that many basketballs? Do you play basketball? No? What sport do you play?
Lacrosse.
Lacrosse. Okay? If you had that many lacrosse balls, how big would the ball bag have to be?
Very big.
How big?
He can fit it.
So it's just the magnitude, right? It just overwhelms you. Turns out about the volume of half the Earth. That's how big that number is. If it was a basketball, it'd probably be the ball bag would have to be the size of the Earth. That's how big that number is. If we had that many pennies, we wouldn't have world hunger. Think about that, right? So the moral of the story is, it's a large number. And we had to come up with this number because these particles are so small. Now, what they did is they based it all on the carbon atom, right? And what they came up with is a way to work with these small particles. And they had to, I told you, they had to invent their own unit, right, called an AMU. What's interesting is if you have a mole of atoms, that would mean you would take this number and multiply it by the number I showed you before, which was called Avogadro's number. That's a famous number. And then you would be able to figure out what 1 mole of atoms of carbon would weigh. So what's cool about it is that mass number that we have on the periodic table is giving us how many grams it takes to get a mole of those atoms. So the number has 2 meanings. At the atomic level, it tells you what 1 little atom weighs in AMU units, but it also tells you if you want to go buy a mole of those atoms, or a mole of atoms of that element, you got to weigh out whatever that mass number is in grams. It's pretty cool. So they set up the periodic table so you can figure out when do you have a mole of those atoms. You just weigh out whatever that mass number says in grams. And you know you have a mole of those atoms. Now, so carbon, normal carbon, if I want a mole of carbon, I know I got to weigh out 12 grams of carbon. That's what carbon 12 is basically telling you. Okay? But here's the problem. That number, that mass number, you got isotopes. So the number they give you on the periodic table is a weighted average that includes all the isotopes. So say you have an atom, like in this case, this atom of copper, there's only 2 kinds of copper atoms. Copper that has a mass of 62.93, which that mass spectrophotometer tells me that for every 100 grams of carbon, you got 69.1% that has a mass number of 62.93. What about the rest of them? Well, this is the abundant isotope. These are the radioisotopes. There's 30.9% out of 100 grams, or 30.9 grams out of 100, that have a mass of 64.93. So what they did for you is they used a mathematical calculation to figure out the mass number they're going to put on your periodic table. That's why it's not a whole number. The number on the periodic table is averaging in all the isotopes. And there's a formula that they use. What they do is they say, okay, take the percentage that mass spectrophotometer machine would have gave me for that specific element, divide it by 100, and multiply this by the actual mass of the isotope you're looking at. And then take the other isotope's mass and multiply by its percentage divided by 100. And if you got more than 2, you would do a whole bunch. Just keep adding the numbers to each other. So it's a weighted average, which is different than just averaging up the weights divided by how many particles you have. This is based on the percentages that instrument would give you. So for example, the number on magnesium on your periodic table, if you look it up, you're going to see it says 24.31. Where did that number come from? Well, it turns out the mass spectrophotometer, there's 3 different isotopes of magnesium. This is the normal one. It's 78.7%. We say that's the abundant one. Should have a mass of 23.985 AMUs. These are the 2 crazy radioactive cousins. They have the wrong proton-neutron ratios. So what you have to do is you have to take the percentage, divide it by 100, that's where that number came from, multiply it by the mass of that individual isotope, and you get some sort of value. You do the same thing for the other isotopes, and then add the numbers together, and you come up with a weighted average. That's typically a tough question on it, because math comes out, right? And once math is involved, everybody gets nervous. You have to know how to do this calculation. Now, what's nice is that you typically might see the question in this manner, okay? Which I'm about to show you. So this number right here, on the top, is a weighted average for all the different carbon isotopes that exist. You might see the question this way. It says, element X has 2 isotopes. The 72% one, that's the abundant one, that's the normal one, weighs 84.9 AMUs. Its radioisotope weighs 87. The average atomic mass, how would you calculate it? Which choice would be correct? D. Why? How did you know?
Because you have to divide by 100.
Divided by 100, right? Divided by 100. And that's typically the level of question. Here's another example, which is the correct answer. Now you gotta be careful. See how they got you now? So now you gotta think. Which one? 1. A, right? Or 1. Very good. Okay. So now we progress. So the question is, what is the right model of an atom? Well, Bohr's model failed in the whole thing about the orbits. That's not how it works. Electrons don't travel in orbits. They just don't. They don't do that. And we could prove that scientifically. But you say, well, then why do we talk about Bohr's model? Because it helps you build the concepts behind the truth. Bohr was the father of understanding, allowing us to understand that electrons have energy, okay? And their energy is quantized. That means every single electron has a certain amount of energy, okay? What else is true? Well, Bohr, all the work, there's a nucleus, and we know there's protons and neutrons in there, and that's where the nuclear charge, the positive charge, comes from. Right? That's all Bohr, with all the work of the other scientists. What he did not know, that is electrons travel in some sort of cloudy area around the nucleus. And this cloudy area is like a region where you most likely will find that electron. So the modern model is based on what they call the quantum cloud model. Right? So, based on all the other scientists, before we go into the modern model, which phase describes an aluminum atom? Okay? 3 is correct. Now, we're going to graduate. What does the modern atom look like? Well, we know that concept of empty space that Rutherford told us is still true. There's a lot of volume here that these electrons travel. Okay? But what they did not know is electrons travel in regions of space. And how can I take Bohr's model and teach you the modern model? I would need a ping pong. I would need a softball. I would need a basketball. And I would need a beach ball. What do you mean, Mr. Lindsay? Well, envision a ping pong is an area of space that inside the ping pong, in the center of the ping pong, is the nucleus. And when we say an electron is in the first energy level, that electron can travel anywhere inside the ping pong. That's how it works. You don't travel around the ping pong. You travel anywhere inside the ping pong. Envision that you could take a ping pong and somehow embed it inside a softball. Right? Now you know how big a softball is, right? Obviously it has more volume than the ping pong. And the ping pong sits inside the softball. An electron in the second energy level can travel anywhere inside the softball, including through the ping pong. Right? Envision the third energy level will be like a basketball. Take the softball, embed it inside the basketball, and if the electron's in the third energy level, it'll travel anywhere it wants inside the basketball. And then the beach ball, the basketball we planted into the beach ball, and if you're an electron in the fourth energy level, you can travel anywhere you want inside the beach ball. You with me? This is what we call the quantum mechanical model. It's basically telling us that these electrons have a certain amount of energy. And their energy is based on what energy level they're in. So if you're in the beach ball and travel anywhere inside the beach ball, you have more energy than the electrons that are inside the ping pong. Because they're restricted how far they can get from the nucleus. Does that make sense to you? So electrons in the beach ball got a lot more energy than the ones that are stuck in the ping pong. A famous scientist, Schrödinger, came up with equations that he could actually map out the areas of space inside these energy levels. So imagine, mathematically, a scientist is able to find pockets of space that you could probably find these electrons outside that nucleus. And he gave a name for these pockets of space. Inside these clouds, so the ping pong cloud, the softball cloud, right, the basketball cloud, and the beach ball cloud, he was able to figure out what we call orbitals. Now, it gets confusing because the word orbit, like Bohr had, and now this new word, orbitals. Orbitals are pockets of space, or regions, to be more scientific, within those energy levels. It turns out, envision that orbitals are kinds of roads that the electrons use as they go through the nucleus, believe it or not. That's what happens to them. They go right through the nucleus to the other side and then turn back. What these guys did is figured out these orbitals or areas within the energy level that you could probably find that electron. So this was a big deal. And that's always a Regents question. The word atomic orbitals. That is the area that you most probably will find that electron. Every electron is traveling in an orbital within the energy levels. And these orbitals of these regions of space have shapes. These orbitals are called s orbitals. They're spherical in shape. So if you're traveling in an s orbital, let's say for example, you go anywhere you want within this. So there's really very minimal restriction in an s orbital. But if your electron's stuck in what we call a p orbital, you can only go side to side of the nucleus. P stands for planar, that's where that comes from. So you can only go side to side. Then there's all these weird shapes. Like you could take those p orbitals and line them all together and envision that the nucleus is here. There are some electrons that can only go along the y-axis. There's some that can go along the x. Say, wait a minute, so Joe, that don't make sense. Well, they're looking from above. I don't know why they do that, but when these were first drawn, they're looking from above. You're looking up above. This is your x-axis, this is your y-axis, and then there's a z-axis in 3 dimension, right? These are areas of space that there's like, and there's even more complicated spaces, more restricted spaces that electrons are bound to travel through. These are called d orbitals. But here's important. The more restricted, the more energy the electron has, because they can't go wherever they want. Envision atoms with 50 electrons never collide. So it's like a musical orchestra where electrons are moving and they never collide because they're restricted on how they can travel. Look at this one. This is even weirder. These are called f orbitals. There's 7 different types of s orbitals that an electron can be restricted to travel. So all those shapes, you don't have to know for the Regents. I showed it to you so that you could understand these little they're pockets of space. The Regents will say something like this, straightforward. A region of most probable electron location in an atom is called? Period. That's all you gotta know. That's all you gotta know. But now you know more. You know there's a whole bunch of different types, right? In fact, there are only one type of s orbital, and every energy level has one of those s orbital restrictions. The p, how about those p's that only go side to side, right? The second, the third, and the fourth have p's in them. Notice there's a pattern, right? The first energy level only has one type. The second energy level has the s and the p. Look at this, third energy level, guess what they have? They got an s, they got a p, and they got a d. And then the fourth energy level, which is as far as we're going to go on the Regents and the SAT2 exam, would be an S, a P, and a D, and an F. So in that beach ball, they got 4 different orbital paths that the electrons can travel in. So in the first energy level, what's the maximum number of electrons that can actually be in the ping pong? There's a formula you can use to figure that out immediately. It's take the energy level that you want to know about, square it, and multiply it by 2. So if we're talking about the first energy level, 1 squared is 1, times 2 is 2, right? And in the second energy level, what's the maximum number of electrons? Well, you take 2, square it, 2 times 2 is 4, 4 times 2 is 8. That's as easy as you can get the total number of electrons that would be in an energy level. Obviously, the question is, there's more to it, right? And I'm going to show you an image that will help you with that. And then the third energy level, since it has all these different restricted paths, right? Each of the types can hold 2 electrons, believe it or not. We're going to show you that. But you can tell me right away how many electrons can fit on there. How many can fit in the third energy level? Total. 3 squared, right? Right? That's 9 times 2 is 18. Very good. And what about that fourth energy level? 32. So as the beach ball is really big in volume, there's a lot of little pockets in there that you can put electrons, and you're correct. So let me show you how I asked you, guess what? What is the maximum number of electrons that can be contained in the fourth and principal energy level? The answer is 32. Did you know that before? Oh, that's awesome. Okay. Well, how about this? What is the total number of occupied energy levels in neon? That means you have electrons in the ping pong, the softball, right, the second energy level. Then what was the other one? Basketball and the beach ball. I like that analogy. Right? How many energy levels does neon have electrons in? 2. How do you know?
Because there's the first one who only has 2.
Right, boy, this right here, right? That's giving you the answer. And this is your resource on the periodic table. So this is telling you in the first energy level, there's 2. That's the ping pong, right? And in the softball, there's 8. That's what they're saying. Now notice they don't bring in the orbitals. They just want you to know the fundamentals on the Regents. All they want you to know that they exist. The orbitals exist. And again, remember about the analogy I just gave you. I used soccer ball and basketball as an example on the slide. But if you're an electron in, let's say, that beach ball that we use the analogy, you could travel all the way through the other balls, right through, right? To the nucleus and on to the other side. And then when you get to the actual barrier at the end, you turn back and you go back to the nucleus. What's really crazy, the Regents doesn't tell you, is that this is called the Aufbau diagram. Turns out it's like a map to understand the electrons, how they've been, when you create an atom, where would the electrons be sitting? Right? Would they be in the ping pong? Would they be in the softball? So it's like a map. Envision, this is the stage, which is the nucleus. And this is the seating reagents in the arena, right? What does this number mean? 1. What's that mean?
First energy.
Very good. Now let's see how smart you are. What does S mean?
The type of orbital.
Yeah, man. Very good. Then notice there's a pattern here. Now, this is weird. You know what's weird? I'm going to tell you something very important. For every single atom, the seating arrangement changes. This is for a map that you can use to figure out where all the electrons would sit. These boxes actually move for every single atom. And that helps us explain something that the Regents wants to know. So, those little boxes are the actual orbitals. Each orbital can only fit 2 electrons. Okay? But there are different number of P's. There's 3 kinds of P's. There's 5 kinds of D's. That's what that seating arrangement was telling me. Right? And there's a bunch of rules that you don't have to know for the Regents. But when you fill in these seating arrangements, for example, this atom would be who? These red lines represent electrons. What atom would this be? Very good. How do you know that?
Because helium has 2 protons.
Right? And therefore should have 2 electrons. You with me? So helium has what they call an electron configuration. Right? Where do the electrons lie? Around the nucleus. And this map is telling us that both of its electrons. Notice that one arrow is facing upward, the other arrow is facing downward. It turns out, electrons, when they move, they spin. When the arrow is upward, means that electron is going clockwise, and its counterpart, that's in the same energy level and orbital, is spinning counterclockwise. And they do that to reduce their repulsion. Because remember, electrons are negatively charged. And they don't want to be in the same probable areas. So to reduce that, they spin. That's that magnetic thing that I started out with that I was talking about. So there's a path that you put the electrons in this map. You start at the lowest energy level and work your way up. Right? So every atom has this electron configuration. And you fill up the bottom levels, and then you fill up the upper levels. Now, this is a neat way to actually know what order they fit in. All you do is write out the energy levels and what orbitals they have, and you kind of say, okay, I got to fill this one up first, then this one, then the 2p, then the 3s. So this kind of gives you like a cheat sheet. Again, you don't need to, sorry about that. You don't need to know that for the Regents, but the orbital concept helps explain some of the science behind some of the phenomenon that the Regents does want you to know. Right? So you can see we talked about a lot of things. Okay. This is one of my favorite. I like this the most. Okay. Yeah. We were talking about electrons can move from one energy level to another. How do you do that? How do you make an electron move? Turns out, because electrons are so small, right, they have what we call particle properties and also wave properties. Because they have energy, what can happen is we can make an electron increase its energy by shooting another particle at it that's a lot smaller than itself. This particle is basically the particle of what we call electromagnetic radiation, a photon. So when we turn on the lights in this room, right, what happens? Electrons are going to get excited. Only certain electrons. Electrons that match the energy of the photons. Now that sounds weird, right? So what I'm trying to tell you is that these photons can be absorbed by electrons. And when they absorb these photons, these electrons actually increase in their potential energy. Right? Here's another weird thing. These electrons can spit out the absorbed photon. So they can absorb photons and spit out these photons. You say, well, what are these photons? What's that about? Okay? Well, while they studied the model of the atom, they also studied how electromagnetic radiation, which is basically energy that's composed of these things called photons. Now you heard, believe it or not, you've seen graphs and charts about electromagnetic radiation before in another science class, before chemistry. And once you start seeing the images about these photons, turns out electromagnetic energy is made up of these photon particles. And what's weird about these photon particles, they travel in think of gangs, okay? They travel in what they call quanta. So what happens, envision, here's my hand, and this is an electron, or this is an atom, or this is matter made up of atoms. And here comes the photons. Every time I strike my arm is when the photons arrive. Okay? Now let me ask you this. Did you kind of get that rhythm? Now watch this rhythm. Which one do you think are photons with greater energy? The first one or the second one?
Second one.
Why?
I'm not sure.
But you're right. Because you're going, ow, he must have already hit his arm, right? Well, there was more energy being absorbed, right? Turns out the photons, what differentiates the photons are their frequency. How frequent do they come, right? So you have, this is very frequent versus that's less frequent. So photons are have measured frequencies, and the frequencies in turn are related to their energy. And there's famous equations that relate frequency to energy, but I'm not going to get into that math because that's beyond the Regents. But what I want you to realize is scientists would love to use these photons to figure out where these electrons are, but there's a problem. Because if you go try to find where an electron is, you're going to end up using these photons, which could affect where the electrons are. So a famous scientist says that's not going to work. So you got to come up with other ways to figure out where the electrons are. Because the actual act of trying to measure where the electrons are using these photons would actually affect the location of the electron. So they had to figure something out. But what they did discover is by moving the electron, kind of like do a before and after thing, you could actually figure out where the electron originated, where it went, on its way back to where it belongs, which is a pretty cool trick. So the frequency of these photons, they can actually monitor it using this graph. Like this is when I strike my arm. This is when I pull back my arm. This is when I strike my arm again. So you can measure the time it takes from this, when the photons hit, versus when the photons hit again, right? And you measure that distance, it's actually called a wavelength, right? And that's related to how many peaks do you get per time would give you the frequency of those photons. And in turn, this is something you've seen before, right? Where would you have seen that? I think it was the course called Earth Science. You ever take that class? Yeah, and they're talking about all these different types of photons. It's like a menu of photons. There's X-ray, gamma rays, X-rays, ultraviolet rays. Then these are the ones that we can see with our eyes, right? These are the ones that actually stimulate electrons in our eyes, right? And then there was like a way to memorize it, Roy B. Give, right? Some sort of trick, right? This is kind of going backwards, right? This is high energy, right? To low energy. This whole graph is plotting, even radio waves are made up of photons, right? And they can travel long distances because they're not as frequent, but they can travel long distances because they have long wavelengths. The longer wavelengths, the greater the distance the photon could travel. So what does that do for us? Well, what we do is we look at these photons, and if you get all the colors, for example, you're basically getting all the photons, you're absorbing all the photons in your eye of all the different type in the visible range. How's that important to our atom structure? Well, what we could do is we can excite atoms, for example. And if you excite atoms and you pass that light through a prism, what a prism does, it basically bends the light into its specific wavelengths. So if I excited atoms here and pass that light, I can actually monitor the electrons jumping up and getting excited, and then on their way back down, they spit back the light in specific wavelengths. Every single atom has their own unique, what we call emission spectrum. That means it's like a fingerprint. So we can use this to identify what atoms we're working with. So, for example, you might have done this experiment in class. You had these little tubes, right? And inside the tube you had an element. And what they did is they basically passed electricity through the tube. And then you had these cool little either glasses on or a device called a spectroscope. And you looked in the spectroscope and you looked at the light being emitted by these excited atoms. So this would be the prism. And there was a little inside the spectroscope. They typically don't use, prisms are very expensive. They use a diffraction plastic that can perform the same thing. Then the light, and then you would look at the emission spectrum, right? And what would it look like? You would see certain colors with a black background. Each of the colors would represent a certain excitation. Now, at the same time, you might have did other experiments. You might have taken atoms, like metal atoms, right, that are stuck in ionic compounds, and put it in a flame. And you would look at the colors of the flame, which would be the emission of the light of the atoms being excited. Now, why use flames versus electricity? Well, nonmetals, it's harder to excite their electrons because their nucleuses have more protons. So you're going to have to go to electricity to get them excited. Versus metals, that their electrons can easily be excited. So even infrared in the form of heat can get them to be excited. And you would get what we call these emission spectra. And this would be for a certain element, this would be for a certain element, and this would be, each one would have its own specific one, because remember those boxes? I told you that the boxes move for every single atom. So when the electron jumps to a specific box, when it comes back down, the distance between the boxes is going to be different for every single element. So every single element would give off its own spectrum. And we could actually determine what elements are present by using the spectrums. So how would the Regents ask you a question? You have this unknown chemical, which is a mixture. And you know, inside the mixture, there are elements, right? And here are the possibilities. Element A, here's this bright line spectra, or emission spectra is another vocabulary word for it. Here's element D, here's element X, and here's element Z. What's inside the mixture? So let's go by process of possibility. This is the emission spectrum of element A. Right? And these are the excitation movements of the electron. It got excited, and on its way back down, it spit out certain wavelengths of photons. Is element A in the mixture? How would we know?
If one is matched.
Very good. So you look at this line and then you go, oh, there's a match, right? Is that a match?
Yes.
Yes. Once you get 2, 3, you know that guy's in there. Okay? But I want to tell you the truth, it has to have all of them to be a fact. And I got a feeling A is in there. Okay, let's look at D. Is D a match?
Yes.
Yes. So A's in there, D's in there. Is X a match?
No.
Well, these two are there. He's there, right? Is he there?
No.
No. Right? Is Z a match? I don't see that one. You with me? Right? And that's how you do it. This is real. This is real. Now we have electronics, right, and technology that can do the computer do this in split seconds, right? But this is how we did it in the good old days. Explain in terms of electrons and energy states how the light is emitted by an excited atom. That you might not remember. So that's why I'm going to continue. Oh, I'm so sorry. Okay, the way it works, how do you get that spectrum? Okay, how do you get that spectrum? What happens? So, when you excite an atom, its electron starts out in what we call the ground state. The ground state, and that's an important vocabulary word, is where the electron should be. Okay? When you excite it, you're going to make it go to what we call the excited state. Now we know hydrogen only has one electron. So based on Bohr's model, this is what, because Bohr was the one that figured this out. But what happened with Bohr, he didn't know about the orbitals. So he could only prove he was right with hydrogen. That's so sad. So the guy was so brilliant. He was able to figure out the colors you would get mathematically. But what he didn't understand is once you start putting more electrons in, once you start putting more protons in, those little areas of space change. So when you excite other atoms, the math didn't work because he didn't know about orbitals. He didn't know that the little boxes that I showed you before changed, right? So it only worked for hydrogen. So when hydrogen gets excited, its single electron can do only certain jumps. It can only jump to specific. Now, in Bohr's model, the boxes were all equal on the first energy level, all equal on the second energy level. That's why mathematically he knew there was only certain possibilities. What's important to note, though, the difference between the first energy level and second energy level is the biggest difference. And as you get further away, the differences in the energy levels get smaller. He figured out when you increase the potential energy electron to a higher energy state, it's going to want to go back where it belongs. On its way back down, there's certain places it could stop. The electron could jump, let's say, to the fourth energy level and then back to the first. When it comes back, it's going to spit a certain frequency of photon with a specific color. And there's all these other possibilities on the way back down from the excited state back to the ground state. So these stops, each of those stops would spit out a specific wavelength and frequency of color. So an electron, when it moves from the ground state to the excited state, here's a Regents question. What happens to the potential energy of the atom? Well, first, what happens to the potential? Let's add an extra question. If Langella was writing the question, say, what happens to the potential energy of the electron when you excite it? It increases. Well, isn't the electron part of the atom? So therefore, what happens to the atom's potential energy? Increases. That's right. That's the logic. Very good. It says, hey, which principal energy level change by an electron of hydrogen atom will cause the greatest amount of energy to be absorbed? C. Why?
Because the higher the jump, the more...
Higher the jump. Very good. The higher the jump. Excellent answer. Right? So those line spectrums are the light energies being emitted, right, from when the electron's in a higher potential energy state going back to the ground state. So when it goes from the excited state to the ground state, that's where you get those colors. That's where you get those colors. And every single element would have its own emission spectrum, right? So this is, for example, hydrogens, right? So every single element would have its own. So now, what's unique about electrons, and this is what the Regents wants you to know, electrons have the properties of
particles and waves.
Very good. Particles and waves is correct. It says, you know those spectral lines of an element? They're caused when electrons in an excited state or an excited atom move from
higher to lower energy levels, releasing energy.
Very good. Choice B. Choice B. So it's going from higher to lower energy levels, and when that happens, it releases energy. Excellent. Okay. So, every atom has an electron configuration. Now, on the Regents, we use Bohr electron configurations, so it's just telling you the grand total for each energy level, but you now know that there's a more sophisticated way of doing it, where this number here represents how many electrons are in the atom. This is telling you the orbital, right? And this is telling you the energy level, which is pretty cool. So there's a more sophisticated electron configuration than what you get on the Regents. The Regents gives you the Bohr configuration. All you're going to see is a number 1 for hydrogen, right? So you look in the little box, the Bohr configuration is say 1. What the Regents want you to be able to do is draw what they call Lewis dot structures for atoms. Ever heard of that before? Right? The Lewis dot structure is basically the symbol of the atom with a dot representing how many valence electrons the atom has. Do you know what valence electrons are?
The electrons in the outer
energy level. Very good. So, when you're drawing these Bohr models, you're going to take the symbol and you're going to put a dot on each side of the atom. It's a good trick to do it that way for each valence electron. So, let's say like helium, now they put the 2 dots together, and it doesn't matter where the dots go, as long as you only have 2, for example, for helium. And that's because the Bohr configuration for helium is a 2, right? And just that, you know, you learned more today about the orbitals, there would be 2 arrows inside that little box. So, for example, lithium. Now, I put the pictures of these elements because you're going to have to start to understand, you know, lithium. What is lithium? If you look at the elements, you got metals and you got non-metals, right? And then you got these few in between called the metalloids. And you got to start understanding, well, metals typically look like, have a grayish color, right? They're shiny, right? You know, there's characteristics that are typically malleable, which we're going to talk about later on in the presentation. But a lithium Lewis dot symbol only has